All right. Hello, everyone. Good morning, good afternoon, good evening. So welcome to another session of time series workshop. We were supposed to meet yesterday, but we couldn't. So thank you for showing up today. I just shared the link to the GitHub account. So we are going to be working on the files week 5. So let me share. Again, maybe if those who just joined may not have seen it. So we are going to be working on today 2 files, 01 and 02, 501 and 502. And then there are 2 data files, CSV files, daily total female births and widget sales. The plan for today is I'm going to talk about MA models. And what I'm going to do is I'm going to start with a very simple example. So we'll first develop a very simple predictive model, which is using the yesterday's actually, in this case, data point to as a prediction for tomorrow. Okay, it's a very simple case. And then we are going to use these predictions to find the residuals. And using these residuals, we are going to set up the moving average process. We're going to get the coefficients of this process. Using the coefficients, we are going to compute the predictions. So that is going to be the first exercise we're going to do. Second, using the same data set, this time instead of using predictions, we are going to directly use ARIMA model, but of course the MA part of that. So that will conclude the first part of the workshop. And the second part, we are going to use a different data set. And then this time we are going to explore this data set. And then I'll show a couple of things there, but which we can use them for other data sets as well. And then again, we're going to use this time Sarimax model actually, but again, MA part of it. I just wanted to use different libraries or different classes actually. And then just to learn how to implement, how to find actually the coefficients for the moving average process. So if you guys are ready, we can start. Again, for those who just joined, here is the link to the GitHub account, so you can find the files from there. You can simply download the files from there. We're gonna type the code together. If sometimes the code is too long, a part of the code is too long, I'm just going to share the that part of the code on chat. Again, please feel free to post your questions. If I don't know the answer, I'll try my best to get the answer. Maybe in upcoming scheduled workshops, we can answer those questions. All right. So this part of the workshop, I mainly got the code from Jason Brownlee's Introduction to Time Series Forecasting with Python book, but I made a lot of revisions on the code. So the code itself right now, if you just simply copy and run it, may not work. Some parts may not work. Okay, so I had to do some work on the code. Anyways, so let's get started. For this part, we are going to use plot ASF and plot PACF, and then when the time comes, we're going to talk about what these two means. Last time, I remember in our last workshop, we have not talked about how we can test stationarity of a data set. So this time we are going to use A.D. Fuller test to see if a data set is stationary or not. And then when we use this test, we can also talk about what stationarity means. The others, you know what they are. So actually, I'm just going to say instead of these, I'm just going to use from import pandas. PD. Okay, that's going to be much simpler. All right, so let's load our data set quickly and then start working on our data set. The first data set we're going to use is daily total female births data set. All right, so my data, it's a CSV file. So we're just going to type the name of the data, daily total female birds .csv. There's a question here. How to know what is the best method? Interpolate linear okay. So in time series data sets, when you have missing values, how to know the best method? Yeah, that's a good question. So in general, for time series data sets, what we do is, in general, if there is a missing value for time series data sets, so far we mainly used either fill forwards or back forward. Means I use the last known data point and then fill all the empty spaces until the next known data point with the last known data point. So that is forward filling. Backward filling is you simply fill all missing values using the last known data point. In between two known data points, use the last known data point to fill in all missing values. That's one way. You can take the average of these two and then use it, or you can use linear interpolation. Means between these 2 points, you can create equally spaced data points and then fill in. All these are used methods. Which one is the best? It depends. It's very difficult to. I mean, I don't think backward filling or forward filling or interpolation, I don't think they are going to have too much of a difference in terms of filling in the values. I don't think they're going to have too much of difference. Okay, so yeah, here is our data set. So when we read the data set later on, I'm going to also first read the data set and do some of the things that I'm going to show here manually. But so let's say index column. Take the first column is index column and then parse dates as true. So this way we are going to change the date column into a date format, the data type of the date column into a date format. So let's see how our data set looks like. My data.head. So as you see, I have one column, birds, and then I have the date column as the index, and it is, so let's do this. We did this before, but I just want to show that, maybe remind that to myself one more time. Say data, for example. Let's just read the data as it is and then see the difference. So as you see, now we have two columns, right? Birth and date. Date is, if you check the data.the types, right? So date is an object. It's a string now. So maybe you need to change it into PD. You need to maybe change it into a date format. But in this case, we're not going to do that. What is it? Manually, we are just going to, when we read the data set, as we are reading the data set, we are changing the type of the data into date type and then setting it as the index column. So we did all that as we are reading the data set. So that's what I wanted to point out. Okay, let's continue. Now we have the data sets. If you like, we can just plot the data set just to see how it looks like. So for that, let's import matplotlib.pyplot splt. Hello everyone. Yeah, so you're welcome, Andre. And then again, those who just joined, this is the oh, I already changed the, yeah, this is the GitHub address. Let me post this one more time, and then I'm not going to interrupt class for this again. Yeah, you can get the files from this address. Okay, so let's now plot our data set here. My data, just to see how it looks like. So why did I do this? I just wanted to see, again, remember from our previous discussions, if there is any upward trend, if there is any cycles, it looks like there is a slight trend. I don't, let's ignore that. Let's ignore that. And then I can see some, I don't know, we need to actually get into, maybe focus on the data sets, zoom in, and then try to see if there are any seasonalities in the data set. But as of now, let's assume that we don't see any such seasonality. I don't think there is any seasonality. By just looking at this data set, I don't think we can easily see it. And it looks like there isn't any trend. So for stationarity, there are three things we are going to check, right? So first, if the data set has what is that? The mean of the data set remains constant across all time points. So if you take any slices from your data set, is the mean going to remain constant? Okay, that's one thing. Or overall, is the mean going to remain constant? Second thing is the variance remaining constant? Is it changing or remaining constant? So that is the next thing. And third, if there is any seasonality in the data set. So if any of these, if the answer to any of these is the mean remaining constant, if you say no, is the variance constant if you say no, and then is there any seasonality if your answer is yes? So then the data set is not stationary. So stationarity means data set remains overall the same. When it says the same, the variability of the data set, the range of values the data set is taken from, that should remain constant across the time. Okay, that is stationarity. So why are we interested suddenly in stationarity? Because if the data set is not stationary, the models that we are going to use later on, like moving average model, AR model, ARIMA model, Sarimax model, so these models are assuming that the data is stationary. If the data set is not stationary, we need to take some steps to make it stationary first, and then use these models to make our forecasting or predictions. All right. Okay. So so this is our data set. Again, we wanted to see visually if there is any seasonality in the data sets. It means there are cycles happening within 1 year. That is seasonality. Okay. There might be cycles spanning multiple years. That is called cycle, actually. Okay, so that's one thing that we want to see visually. Second, if data set was moving upwards, we might think about mean being not the same, right, across different time points. Or if the data set is showing some small variation at first and then suddenly showing high variation at later points, that also visually will show itself, and then we will say, no, data set is not stationary. But at this point, visually, it's very hard to say if this is not stationary. It's very hard to say that. So for that, let's do the ADF test and then see what the test is going to tell us. And then maybe we can also talk about the test result a little bit. Okay, so what I'm going to do is I'm going to use ADF test. So for ADF test, as I said at the beginning, we need this, what is it? From stat models, TSA, stat tools, we need this class called AD Fuller. Last time I told you that I tried to write the code for this manually, but I need the ADF distribution. It's not, I'm not going to be able to use T distribution directly. So for that reason, I just gave up. Okay, I didn't do it. Okay, so first let's run the test, see the result, and then talk a little bit about this test, a little bit about ADF test. So I'm going to say ADF Fuller. Okay. And then I'm going to put my data. All right. So let's see what this is going to return to us. It's not defined. Let's run this. Okay. So I got the results. Of course, there are a couple of things here. If we don't know what is what, it's going to be very confusing. So what I'm going to do is I'm going to take the first one. From this, it returned a tuple. I'm going to take the first element of this tuple. Okay. Let us also take the second element. All right. Actually, these are the two which we are most interested in. All right. Okay. So the first one is actually the test results, ADF results. So let's even write this nicely. Print ADF results. Okay, so let's write, I'm sorry. This is the ADF test result. Test result, the more negative, the better. Okay, let's say this, and then print the p value. What is that p value? Okay. What is the So the test result is -4.8, and then p-value is a very small number, 5.2 times 10 to the power of -5. So when we run this test, the null hypothesis is the following. There are two hypotheses we are testing. Okay. Null hypothesis is that the data set is not stationary. Okay, so we are going to talk about this, and then the data set is stationary. Actually, this is not the exact hypothesis we are testing. What we are testing is that there is the unit root. Okay, that means the data set is not stationary. And then there is not unit root. That means the data set is stationary. All right. Then the question is, what is this unit root and what is this not unit root? So let's just talk a few words about it, and then we'll move to the next one. So when we are talking about time series data sets, there are two main processes actually we are going to talk about: moving averages and auto regression, right? These are the two things. One is MA, the other one is AR. Okay, so when we put these together, it's going to be ARMA, and then in the middle, when we insert I integrate, then it's going to be ARIMA. So when we add seasonality on top of that, it's going to be SARIMA, and then when we put exogenous variables, it's going to be SARIMAX. So we start from MA or AR, and then we just add, and then have one complete time series model. So this auto regression or moving averages, each one is one topic. Today we are going to focus on moving averages. But what happens with moving averages? I just gave the description below, and then I also gave the description above. Is the data point at time t, and t is now, let's say, is equal to some constant. Okay, the constant can be 0, some constant plus the error term of time t. Let me make that a bit bigger, and then error terms from previous periods, t-1, t-2, and q is how long back we are going to go back. Okay, how back we are going to consider the error terms from previous time points. So q is going to tell that information to us. All right, so let's say I will consider error term of now and only error term of the previous period, then my q is going to be equal to 1. I only consider one lag when I set up my MA model. So this a little bit counterintuitive at first. So what does that mean? So what is this error means, right? What does that mean, error term here? We don't know that error term. By the way, another thing I wanted to do for you guys is, can we create this MA model again from scratch? So if you look at this model, it's not different than any linear regression model. If you guys studied linear regression, this is beta 0, and then this is some error term, and this is one of the variables, one of the features in your data set, and that is the coefficient of that, right? So this is not so different than, so beta 0, beta 1, beta 2, beta q, and this is the error term. It's not so different than linear regression. Actually, if we had known these error terms, we could easily fit a linear regression model that is no different than MA model, okay? But the problem is we are not going to know these error terms. So what is the error term of t? So if I had a prediction, let's say y hat t, and then if I know the true label for time t, let's say I'm considering stock prices for today, right? So I know the stock price for today if it is realized already, and then I know the prediction for stock price for today, the difference will give me the error, or let's call it residual at this point. To simplify this, we are going to, so to simplify this, not we, but people who were setting these models, they said these error terms are actually, they assume that they are coming from a normal distribution, let's say, with zero mean and standard deviation one. So these are some error terms which are independent from each other, and they're coming from zero mean and standard deviation one. What is that? It's the normal distribution. Remember our discussions on random walk? I think it was the third lecture, third session. So this is how we set up the random walk, if you remember, right? So what we did was today's observation was a function of yesterday's observation. And if you are simply using white noise, right? If you are simply using the standard normal distribution as your observations, so you can create random walks simply using standard normal distributions. Again, remember our discussions from previous sessions. So our job as data scientists here is trying to figure out these coefficients. Once I know these coefficients, well, the model, the ARIMA model is going to help us make the predictions. We're not going to do this manually, but today we're going to do this manually as well. Okay, so see how we can make the predictions once we know these coefficients. Okay, so this is the MA model. The AR model is a little bit different than this. AR model is when I say different, instead of error terms, we are using the data itself. So instead of error term t minus 1, we are using y t minus 1. So that is auto-regression. We are regressing. We are regressing on the data itself to find the data point for today, or to find the next data point, to forecast the next data point. So let me use a very simple AR model, okay, just to complete this discussion on ADF. So let's say I'm going to use Markdown, okay. So let's say A of t, okay, is equal to A of t minus 1 plus some error term. And in front of A of t minus 1, I have the coefficient theta, okay? All right, so let's say this is our autoregression model. It's a very simple autoregression model with lag 1, means the data value now, I'm using A, but let's use Y so that it's going to be more compatible with what we are doing. So YT is a function of YT minus 1 multiplied by some coefficient plus some error term. So I can easily turn this into, by the way, I can easily turn this into this format. Okay, I can easily do that. Okay, let's say this is our simple model, and I don't know if you guys are having the same problem. Nowadays, I began to have this problem of suddenly SL is disappearing. So what I want to do is I want to write this expression starting from the very first data point. So if YT is equal to theta times YT minus 1, right? Then I can write the, let's say Y2, okay? Let's say, let's start from Y1. It's gonna be theta, right, times Y0 plus E1. So this is the first data point, right? So in terms of being a function of previous data point, because there is nothing before Y0, so I'm not gonna write Y0 in this format. So then if I write y2, right, y2, again, it's going to be theta times y1 plus E2, right? So what's going to happen is I can simply replace theta times y1, right, by theta times y0 plus E1. Let me first run this so I'll show you what I'm writing. So y1 is theta times y0 plus E1 times y2. Yeah, you see, it's suddenly disappearing for some reason. Maybe I don't know why it is doing that to me. Okay, so this is y1. I really don't know why this is happening. So what I want to write here is, can I write yt, or let's say the last data point at time t, in terms of y0 and then y1 and then y2? If you actually write it that way, what you're going to receive is, at the end, what you're going to receive is, let me write that expression, and then hopefully this will be done. So yt is equal to theta to the power of t, okay? And then it's going to be y0. That is the first data point, right? And then plus summation of from k equals 0 to t minus 1 error term t minus k. Let me, yeah. So this is what I was trying to get from here. Let me write one more here so that you know what I mean. I'm just going to copy this. This is y1, and then I'm going to write y2 in terms of y1. y2 is theta times y1 plus E2, and this is equal to theta times, instead of y1, I'm using theta times y0, so it's going to equal to theta times y0 plus E1, and this is E2. Okay, and this is equal to theta to the power of 2 y0 plus, I want to make a point here, so I'm sorry for this math for now, and then we'll be done with this. Okay, now let me make this mark down. All right, so I just gave the equation for the first two data points, for first three actually. This is y0, this is y1, y2. I wrote it following the same expression. I wrote y2 in terms of y1 and e2, and I wrote y1 in terms of y0 and e1, and finally y2 is theta squared y0 plus theta times e1 plus e2. So these error terms are here, and this theta squared term is theta to the power of t for the tth data point. Okay, so that is what we received for a very simple AR1 model. Now remember, for stationarity, we need three things. Mean should be constant, variance should be constant, and there should not be any seasonality. So let's put seasonality aside for now. Let's focus on mean and variance. So this theta is what we are focusing on now. Okay, so this is the coefficient that we are focusing on. And when I say here unit root, what I want to actually check is if this theta is equal to 1 or if theta is less than 1. Okay, so what I want to check is if theta is less than 1 or theta is equal to 1. If theta is greater than 1, then if you look at this equation here, as I add more and more data points, you will see because theta is greater than 1, a number greater than 1 to the power of t, so this yt is going to get bigger and bigger. That means the mean of the data set, when you plot the data set, the mean of the data set is not going to remain the same. The data set will explode, actually. It's going to increase and increase, right? So if theta is less than 1, again, mathematically, we can show this. If theta is less than 1, so in that case, the expected value of yt for theta being less than 1, right? If theta is less than 1, this is going to be this term plus expected value of error terms is 0, so this will go away. So expected value will be equal to theta to the power of t times y0. If theta is less than 1, remember from geometric series, right? It's going to be 1 divided by 1 minus theta, right? So this is going to be a constant if theta is less than 1. This term is going to be constant. Expected value of this term is going to be constant, all right? So in other words, if theta is less than 1, this time series data set is going to be considered as stationary. If theta is greater than 1, it's not stationary. If theta is 1, the question is it going to be stationary or not? If theta is 1, so it's going to be the mean is going to be constant because theta to the power of t is 1. 1 times y0 is y0. And these guys are actually expected value of the error terms is 0. So mean is going to be constant. But the variance is not going to be constant. The variance is not going to be constant. The variance of error terms is sigma squared, and then I have t minus 1 of these guys. So the more t I have, the more variance I have, right? So that means the variance is not going to remain constant, and it's going to be not stationary. So theta is 1 is something that I don't desire. So I'm just testing if theta is less than 1 or theta is greater than 1. Okay, so that's what I want to test using this AD Fuller test. The test is testing this hypothesis where there is a unit root or there is not a unit root. If there is a unit root, data set is not stationary. If there is not a unit root, data set is stationary. So the alternative hypothesis is the null hypothesis is rejected if p-value is really small. Okay, so that's why we are checking the p-value and it's very small. Then we reject the null hypothesis and then we accept the alternative hypothesis, which says there is not unit root. So this is actually just a very basic, very quick overview of why we are running this ADF test. Okay, so if you are interested in details, you need to we need another session for this if we are interested in the details. But this is on the very surface, okay, roughly what ADF test is checking. Of course, we might have more than one thetas. In that case, it's going to be augmented DF test. That's why we call it augmented, because once we have multiple thetas, like theta y0, but we might have theta y1 as well. So theta 1, theta 2, theta 3. So if the lag is not 1 here, if the lag is not 1 but more than 1, then we're going to have augmented. But again, what we are testing is if those roots are summing up to a unit value or not. All right, so that is what the ADF test is about, roughly. We checked for our data set, and then we found that our p-value is less than is a very small number. Okay, that's one indication that our data set is stationary. Okay, so let's also plot our autocorrelation function. Again, I think the second week we discussed autocorrelation function. Let's plot our autocorrelation function and then see how our data set looks like. So for that, I'm going to be using plot ACF, okay? And later on, I'm going to use plot PACF as well, and then we'll talk about the difference between these two. So let's plot autocorrelation function of my data. Okay, so as you see, my data is in the autocorrelation function. Why this is giving me two figures? So the first one is lag 0. Lag is equal to 0. We always expect autocorrelation of our data set with itself is going to be 1. So the second lag means the autocorrelation of our data with t minus 1. So what we do is we take our data as a series, as a vector, think of it as a vector. We shift our data by 1 and then take the correlation of these two columns now. So that is the autocorrelation for lag equals 1. And this is autocorrelation for lag equals 2. All right. So if my data was seasonal, the autocorrelation function would also show you some seasonality. So one thing I notice here is somehow, right? So it looks like there is a slight seasonality here. So we're going to explore that later. It's every 7th or 8th, suddenly the autocorrelation function, the magnitude becomes bigger and then gets smaller and then gets bigger, smaller, and then gets bigger again. So it looks like there is something going on. There is something, it looks like something is going on. So all these autocorrelation values for these lags, which are contained within this shaded area, means those autocorrelations for those lags are not statistically significant. They are not so important, right? So from time to time, you might have high values at very long delays after very long lags. Okay, so many lags, and then you said, so you need to be careful about that. That might be just pure chance, randomness, or because of seasonality. Okay, because of seasonality. For example, if it's a yearly seasonal data set, right? So then you're gonna see a correlation function high, let's say at day 1, and then you're gonna see another correlation high 1, say at day 366, right? So that is, if it is monthly you see a seasonality which is showing cycles every 30 days, then at the beginning of each month, right? So you're gonna see the same maybe correlation or similar correlation values. So that's one thing that we are gonna see from our autocorrelation figure, the plot. Second thing is, and this part is going to help us determine what type of model we are going to use. If our autocorrelation function abruptly, okay, suddenly decreases after first couple of lags, so this is a good indication that maybe we are going to use moving averages. Okay, that's a good indication that we are going to use moving averages. Again, there is some we can discuss on why this is the case. But for now, please take this as a sign that if your autocorrelation function is suddenly going down after 2-3 lags, so it's an indication that maybe you should use moving averages model. If your autocorrelation function is the lags are slightly or getting smaller and smaller, and then after a while they are getting lost, right? So that might be an indication that you should maybe use or utilize an AR model, autoregressive model, right? Autoregression model. So this is another thing that we get from the autocorrelation function or autocorrelation plot. So later on, we're going to use a partial correlation plot as well, and then we're going to talk about it, what we can get from that plot. So for now, what I see is I'm going to use maybe lag 2, maybe lag 3, but lag 2 for sure for my model, okay? But if I'm going to use any MA model for my data set. So that's what I got from this data set. So maybe we can say we can also plot PACF. Let's see. Plot. Let's see. Let's use the flags. I don't know. So I just wanted to see a wider area. So the PACF is not coming so different than my autocorrelation function. So maybe it is a good time to talk briefly about the difference between ACF and PACF. ACF and PACF. So what is the difference between these two? So what happens is when you look at time series data sets, the data points, we expect them, right? So in a time series data set, we expect sequential data points have an impact on each other. So say you are taking the number of tickets sold in a theater, right? So today, number of tickets today sold is not independent from the number of tickets we sold yesterday or the day before yesterday, right? So if it's an increasing trend, we are going to see that we are going to be part of that trend. If it's a decreasing trend, we are going to be part of that trend. So today's sales will be dependent on the yesterday's sales, maybe the day before yesterday's sales too. Okay, so that's the first thing. Today's sales might be dependent on 1 week before sales as well. Okay, so that means the data point at time t, okay, can be dependent on data point at time t minus 1, data point at times t minus 2, blah blah. So these t minus 1 and t minus 2 will determine how many lags we are going to consider as the data points from past are having direct impact on today's data points. So I just use the word direct impact. Okay. So for this, we are going to use this direct impact. To measure the direct impact, we are going to use partial autocorrelation function. So when I say direct impact, this is what I mean. So the impact of yt minus 2 on yt is happening in two ways. Okay, it's happening in two ways. So yt minus 2, let's say the sales from 2 days before, is going to have an impact on the sales today, but yt minus 2 also will have an impact on yt minus 1, and yt minus 1 will have an impact on yt. So the impact of yt minus 2 on yt is happening in two ways. One, yt minus 2 might have an impact on yt directly. Something happening here might have an impact on yt. And also something happening here has an impact on yt minus 1, and so yt minus 1 has an impact on yt. So the impact on yt minus 1 from yt minus 2 has an impact on yt. So that is the autocorrelation function, is combination of all these impacts. Okay, the impact of yt minus 2 on yt indirectly or directly. That is autocorrelation function considers the impact of yt minus 2 on yt coming from in all directions. Okay, but partial autocorrelation function focuses on the direct impact of yt minus 2 on yt. So that's why when we are developing an AR model, right? AR model is yt is equal to B0 plus B1 times yt minus 1, right? So this is an AR model with lag 1, right? AR1, right? So as you see, I am considering the direct impact of yt minus 1 on yt. So I can even write B2. Let's say it is AR2, yt minus 2. So as you see in this model, I don't see anything that yt minus 2 is having an impact on yt minus 1, right? So basically, I'm just considering what is having an impact on yt minus 1 and yt minus 2. They're individual impacts on yt. So because of that, when we consider how many lags we are going to use for our AR model, we are going to check our partial autocorrelation function plot, right? But if we are considering the cumulative effect of previous periods on today's period, so let me use the error term for that. Yt is equal to again mu plus error term of today plus error term of t minus 1. So this error term t minus 1 has all these different impacts of yt minus 1, yt minus 2. So these error terms. Okay. So again, I need to have a coefficient here. Let's use c theta 1, and then I can not this multiplication, and then I can even use theta 2 times e t minus 2. So this is lag of 2, ma2, right? So for this one, use partial correlation. And for this one, use ACF. Okay. Again, when we come to ARIMA model or Sarimax model, we are not going to individually, maybe that's another thing that you need to make hyperparameter tuning and then find the best the number of lags that you're going to consider for AR and MA partial part of your model. But if you want to explicitly say, here is the P value, which is the number of lags we consider for AR model, here is the Q value, which is the number of lags we consider for MA model. Then we need to check our partial autocorrelation and autocorrelation functions. Right? Okay, let us continue. I know that we are talking about this and that. No, want the error terms coefficient p theta to the power of k. Let's see. This one, right? Yeah, that is right. Yeah, I was a little bit surprised then too, because when I was trying to explain, the variance is going to be bigger when theta is greater than 1. So I was also a little bit confused that there must be some so this is theta to the power of, let me see, theta to the power of t minus k. Let me write it correctly. Thank you for the correction. I just saw your Priyansh, I just saw your message. Thank you for this correction. Let me correct this one. So if theta, very strange error. I don't know so that must be something simple, but I couldn't get the reason for that. Let me make this theta. Yeah, when theta is less than 1, this whole thing is going to collapse. When theta is equal to 1, then this is going to be again theta to the power of t. So the variance is not going to remain constant. Yeah. Okay. So let's go back. Let's go back to our discussion on ACF, PACF. What we were doing here, we got the ADF test result. We got the plots of ACF and PACF. We discussed briefly on how we can use autocorrelation plot and partial autocorrelation plot and what they mean. Again, very briefly, I strongly recommend you guys do some reading on this, or maybe watch some lectures on PACF and then ACF explaining them in detail. Okay, now let us create a simple model first for our problem. Okay, and then we're going to use the residual errors of that model, and then we are going to use create an MA model, and manually we are going to make the predictions using the coefficients values. And then we are going to use ARIMA model, train an ARIMA model. And then I'm going to train a Sarimax model. And then if we're going to try if we should make some seasonality adjustment on our Sarimax model. So this is the flow of what we're going to do next. It's going to be a little bit coding. So please try to follow as much as you can. And KT, if I was to create a time series forecasting for different clothing items for a high street brand, do I create separate time series forecasting for each clothing item? Is this the only way I carry out this? So you are creating a time series forecasting problem for different clothing items. Consider these items. You need to consider if the sales of these items are impacting each other. If they are not impacting each other, you can consider totally different models for these guys. But if they are impacting each other, then your model should include the sales of for the other items as well in your model as a independent variable. Yeah. If they are substitutes. So I developed a time series model, KT, similar to this one for movies. I don't know if you guys remember Blockbuster, the movie rental company. So at the time, when you are developing a model to predict how many, physical DVDs you are going to ask from the movie studios, right? So this is also a function of how many movies are released in that week, the genre of the movies. So it's not independent, right? So the number of the number of people going to theater to watch a movie, right? It's not totally independent of other movies released in the same week. So you have to consider them too in your model. prediction output is for multiple independent time series impacting your prediction. Yeah, that might be Rupa. That might be one model to go. I mean, you can explicitly write your model as a that's one way I will solve as a regression problem. But in your regression problem, the independent variables will be delayed versions of current sales and then sales of substitute products. So that's what we tried to solve the problem at the time. Yeah. Sorry for giving very brief. If your model for forecasting sales of item A also includes sales of item B, how many lags of item B should also be included? So those are very, Michael, this is a very specific question, very specific question, very hard to answer this question. Item A, so I would consider the same number of lags for item A and B if item A and B are interacting with each other. Yeah. Would this be a multivariate time series or a panel data time series? It's gonna be, when you say panel data time series, so it's gonna be a multivariate time series. You have multiple, hold on. Yeah, it's going to be, I think you can solve using both, but again, I would try to keep things simple on my side. So that's how I would address this problem. So I will use a panel data time series where I can use the substitutes as independent variables. Okay, let me continue with where I left. So this time I'm going to use a persistence model for BERT's data sets. Let's create the model very quickly. Again, here we are going to do some coding. So let's remember our data. This is my data. Okay, this is how our data looks like. It is a data frame. Okay, it's a data frame. So what I'm going to do is I'm going to take my data frame and then shift it by one. And then let's see what happens when I shift it. We did this before, if I remember that. So if you shift it by one, as you see, your data at let me put these two together. So that's pd.concat. My data, my data shift by one. Okay, then this is going to happen in terms of columns. Yes, I just want to show you how they look like together. Yeah, here is the data set, right? So here is the BERT's data set, a BERT's column. This is the BERT's column, but it is for t+1. So I just shifted the column by one time period. So let us assign this to df, okay? And then let us assign new columns to df, okay? So this is gonna be t+1, okay? And yeah, because I already ran this line of code before, this gave me an error. So let me run this one more time and then go back here. Where is that? df is, am I having a problem? Oh, they have columns equals, I'm sorry. Okay, so we got the data frames, data frame actually. Now what I'm gonna do is I'm going to split my data into two, and I'm gonna use the values of my data points. So let's say X is df.values. So the moment I do this, here is how X looks like. It's a multidimensional array, okay? I just took the values of data frame. It's a multidimensional array. I lost the time index at this point, okay? So let's say my train size is length of X times 0.66, but let's turn this into an integer. Okay, so this is the train size. I'm going to split my data into test and train data points. So the train data set, will be from my data set. I'm going to select everything up to train size, right? And then I'm going to select the first one because select from the second row because the first row has an empty value, right? NaN. So I don't want to say. So let me show you. Right? This is the first row. First row has a missing value because I shifted my data. I don't want this, so that's why I start from 1. Let's also put test in here. It's going to be X from train size till end. So what I did is I took my data set and then I took the first 66% of my data points without because my data set is ordered by time, right? So I took the first 66% and then assigned it to train without shuffling. I didn't shuffle my data set. If I shuffle, then I lose the time component there. So this is my train and test data set. Okay, I divided my data into 2 pieces. And remember, train and test, they both have 2 columns, column 1 and column 2. Actually, column 1 is, in this case, remember for when you write your machine learning models, right? You have the X and Y. X is feature sets, right? Y is a target, right? The label or the label. So here, what we are doing is using, we are predicting today's value by using the yesterday's value, right? We are predicting today's value by using the yesterday's value. So that's why what I'm going to do is I'm going to split train data set into train X and train Y such that the train data sets, the first column will be the train data set, and then the second column will be the label. Train. Okay, again, let's think about this, what's happening here. This is our training data set. I'm going to take the first 10. Okay, so this is my training data set. Remember, this is T plus 1. Let me use DF. Okay, so this is DF. Again, the first 10 rows. This is T plus 1. So what I do is my prediction for T plus 1, okay, my prediction for T plus 1 is the value from T. Okay, I'm going to use today's value to predict for tomorrow. Okay, I'm going to use today's value to predict for tomorrow. In that case, T column will be the feature set, T plus 1 column will be the label. Okay, my prediction, right? So that's why the first column is capital X, the second column is assigned as Y. Okay, so this is the first column and this is the second column. All right, so let's run this. And we'll do the same thing for test data sets. Let me just copy this. Okay, so we are going to copy this code later on. So we're going to write this part only once, so we don't worry about it. Now I'm going to write my predictions. Okay, so the predictions are going to be that what I'm going to do is I'm going to go through the test data set. So test X. So let me show you how test X looks like. Test X. Let's check the first 10 data points. Okay, so this is test X. Test X is, this is time T. So given today's 51, okay, I'm going to predict tomorrow's value. So given today's 51, I'm going to predict tomorrow's value. So what I'm going to do is today's value will be my prediction for tomorrow. So that's why my predictions are nothing but whatever I have. So I'm going to go through my test data set. Whatever I have in my test data set, that is my prediction. Okay. Whatever I have today is prediction for tomorrow. All right. So this is my prediction. Okay. So X test, test X, not the X test. Okay. I hope this part is clear. This is a very, very naive predictive model. All right. Now, I'm just going to compare test Y. Remember, test Y is the label. Test Y is the second column of my test data set, which is the label, which is what actually happened in terms of, in this case, the data set is number of female births, daily number of female births. So imagine that you are at time t. Okay, let's do this way. Time t plus 1. Okay, we are going to make our prediction for time t plus 1. What we do is use the value from time t, which we are at time t. So we are going to use X test t as our prediction for Y hat t plus 1. Okay, so this is what we did. Using X test t, I assigned this as my Y hat t plus 1. Now I'm going to compare Y hat t plus 1 with Y t plus 1. So what is Y t plus 1? The actual value at t plus 1. What is Y hat? My prediction. So that's why I'm going to take the take Y value, which is test Y, take Y value, and predictions, which is Y hat. I'm going to put these two into what is that? Mean squared error. So what is mean squared error? I should have gotten that one here. Scikit-learn metrics mean squared error. What it does is it subtracts these two. It subtracts these two, takes the squared, and then takes the mean of that. Mean squared error. All right. So let's take the square root of this. For that, should have, yeah, from math square root. Okay. Take the square root of this. All right. I think we are almost done. Yeah. So this is the mean squared, the square root of mean squared error. So again, we subtracted each of these guys. We subtracted Y hat t plus 1 from YT plus 1 for all data points in the test data set. We subtracted them. We took the square root of the subtraction, summed that up, added up all these squared subtraction terms, and then took the square root of that summation. So what does this tell us? What does that mean? So I'm going back to my data. Remember, I plotted my data. Look at my data here. Right? This is the plot. Look. So in general, the data is, the data is in between, let's say, I don't know, 25 to 55, sometimes 65, 75, 85. So this is the numbers, but there are small numbers too, 45, 35. So these are the numbers. So what I found is my predictions have on average a difference. My predictions have on average a difference of 9 from the actual value. So 9 is a big number here. If you consider the range of values, the true values are taken from, 9 is a big value. In other words, this prediction is not so good. Okay, this prediction is not so good, but it's okay. It's a very simple prediction. All right, it's a very simple. Let's keep this prediction aside for now. Yeah, so Raj is asking how would you incorporate cyclical nature, for example, what happened during last quarter of last year is more important forecasting demand for the next 2 months of last year than what happened during the last 3 months from now. So there are different solutions, Raj. There are different approaches to this one. Again, you can incorporate seasonality into your models if you are using Serimax. If you are using some other statistical models, we are using weights for that. So you can assign different weights to different time points. For example, you can consider last week's sales more important than 2 weeks before, sales from 2 weeks before. So you can assign different weights. Weighted, you can, when you are using data points from past, the weights will be different. Right? So to the direct answer to your question, if we are talking about seasonality, then we're gonna use ARIMA model with seasonality. So we need to also incorporate whether we are gonna take the difference of data. For example, whether I'm going to subtract today's data from 1 year later's data so that I can eliminate seasonality, that is difference. Am I going to consider lags? For example, when I say lag, I'm not considering yesterday from today. I'm not considering yesterday data. Lag 1 for seasonality, in that case, if my seasonality is defined as 365 days. So lag 1 means I'm considering 1 day before the same day last year. Okay, so that's seasonality. So I understand all these questions, the questions that you guys are asking are very, very good questions, actually. And then sometimes they may be difficult too. But it also depends what kind of question you are trying to solve. For example, if you are trying to predict or forecast, again, going back to a problem I studied before, forecasting the Uber requests, right? So then what happened 30 minutes before is much more important than what happened for the 6 hours before, right? So in that case, you're gonna put more emphasis on the last 30 minutes, and then the 30 minutes before the last 30 minutes, and 30 minutes before the last 30 minutes. So the last 30 minutes time periods may be a lot more important than what happened six hours ago. So in that case, you might put some different weights. You can use weighted versions of the statistical models you are using. So at least that's what we did at the time. Thank you. Okay. Yeah, this is how we should interpret. So somebody might give you a linear regression problem, all right? And then you solve the linear regression problem. There are certain metrics. For example, R squared is one metric. This RMSE is another metric, okay? Root mean squared error. You take the difference between predictions and true values, take the squared, add them up, take the square root of them. So somebody might ask you, what is this 9.15? What does that tell you? Is this model good or bad? Then you need to check the range of values your data is taking, and then compare that value with this. So that means every time I make a prediction, my prediction might fall 9.15 below or above on average the true value. So if I'm predicting something in the range of 2000, okay, so I think this model is pretty good, right? So I'm again, depending on the context too. If you are predicting the percentage increase that you expect in stock prices, that will be a disaster. 9.15% difference might be a disaster, because people are going to make trading with a couple of percentages, right? But again, depending on the context, let's say I'm predicting house prices. Well, for Bay Area, at $9,15,000, it's nothing, zero. So that means this is an extremely successful model, right? So that's how you're going to answer these kind of questions, whether your model is good or bad. All right, let me continue. Okay, let me continue. So now we got this model, which is very simple, extremely simple. What we want to do is next, we are going to take the difference between our predictions and the true value, again, using this simple model, okay? And then we are gonna call this residuals. And for these residuals, we are going to create this MA model, okay? Normally, you don't need to do that. Normally, you don't need to take the difference between your true values and then these predictions. You can directly use your data set in an MA model, but we are just continuing with what we started, and then we are just asking ourselves, can we do better than what we found in here? Okay, That is what we are asking ourselves. So at this point, what we want to do is we want to introduce an auto-regression for the residuals. It is nothing but an MA model. An auto-regression of residuals is nothing but an MA model. Again, going back to our MA model, the description of MA model, right? So we are now focusing on this part, and what we are trying to do is error at time t is equal to theta 1 times error t minus 1. It's basically an autoregression model for error terms. This one, error at t plus 1, it's not t, then t plus 1 is error plus t, error of at time t, and function of error t at t minus 1. So we are trying to predict these coefficients. It's an AR model. So we are doing MA model actually, but inside MA model we are using AR model. Okay, so the problem is an MA model, but we are solving this problem using an AR model. It's okay. So because today my goal was covering MA, but this is a good opportunity for us to also see how AR is working. All right. So I'm going to use my predictions. So I think we got the predictions here. Like these are the predictions. So what I'm going to do is I'm going to find the difference between my predictions and what is that? True values. But these predictions here are for test data set. So let me find the predictions for train data set because I'm still training the model. Okay. So let me call this train predictions. Predictions. And then this is going to be X. And then, of course, instead of test, I'm going to say train. So basic, again, please remember what we are doing. We are predicting tomorrow's date of birth, the birth numbers using today's birth numbers. Actually, my prediction for tomorrow is what I know today. Okay, that is my prediction. This is train. And then using this, let's find the residual. Okay, so residual is nothing but difference between my predictions and the true value. Okay, again, let's use this list comprehension. So what I'm going to do is for I in range length of my train predictions, okay, for each and every row in my prediction. So not row now, it is a list. So each and every member of my prediction and then training data set, I'm just taking the difference. That's all. Train yi minus. You can do this in a different way, but because these are lists, I'm using list comprehension. Train prediction I. Sorry. I hope this part is clear. So I'm just subtracting my prediction from the true value and then putting this, creating a list for it. So okay, so this is how my train residual looks like. So let me try to plots. This is how it looks like, the residuals. Okay, so sometimes they are negative, sometimes they are positive, depending on if I overestimated or underestimated. Okay, so this is, and then residual here, I mean, visually, it's very hard to see any cycle. So if you see a cycle in your residuals, that's a good indication that you missed something in your model. Okay, if you see a cycle, it's a good indication that your model is missing a significant component. So you need to go back and then make corrections in your model. Okay, so this is my residual. So what I'm gonna do is now I'm going to create a train what is that AR model on my residual. So for that, I'm going to from stats models.tsa. Okay, and then later on you will see that you don't need to use this AR model. You can simply use Sarimax model for anything. But let's use it for now. I'm gonna import from this model, from AR model, I'm gonna import auto regression, and then I will use the word AR. Okay, I'm sorry, AR. Okay, let me run this. And now it is time for me to introduce my model. So my model is going to we trained using the residual data set, train residual, and I'm going to use 15 lags. So again, going back to my partial autocorrelation, actually, I need to, let's do this way. Let us do this way, guys. Because I'm using an AR model, I'm going to create PACF of train residual. And of course, this is not this is a list data set, so that's why we don't see the what is that? Yeah, okay. So that this is the residual. Okay, it is not the data itself. This is the residual. So what I'm gonna do is here you see there are some significant ones in here. There is another significant one in here. So I'm going to consider the first, you can consider maybe first 10 or first 15. I'm using partial autocorrelation plot because I'm creating an AR model, okay? Autoregressive model. So these numbers indicate that these lags are statistically significant, okay? I'm gonna use these ones. And then after a while, they become insignificant. So there is one in here. So let's see. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let me use, even if I can use the first 10, it's going to be okay. Let me use the first 10. I'm going to say lags equals 10, okay? 10. Okay, let me run this. Now I have this object, AR object, which is the model that is ready to be fit. So let me take my model. Of course, let me make this equal to my model. Let's call this model 1. And then I'm going to take this model 1 and then fit it. So it's a little bit different than scikit-learn. Remember, with scikit-learn estimators for machine learning, you will first import the model without the data set. And then when you are fitting, you put the data set as, what is that? As the parameter, right? Parameter of the model. Here, it's a little bit different. So let's call this model 1 fit. Okay, so I got my model. Now let's see what this is, okay? For that, I need to, I want to first see the lags and then the coefficients. So for that, let's see if I need anything that, I think I'm fine. So let me see the lags, model 1 fit, AR, lags. Let's see if this works. Yeah, these are the lags that are considered. So let's take the length of this. If you are working with time series models with Python and then using stats models, these libraries changed in the last 3 years. So, I mean, if you are using code that is from 3-4 years before, you might see that there are some slight differences. So don't be surprised. You need to search and then replace the code with new, some small changes, all right? So don't be surprised. Okay, so this is lag. So this 10 is the window that I'm going to consider when I make my predictions. Now, please keep in mind, when you are making predictions using MA or AR models, your forecasting window, which you're gonna make predictions for the future, is not gonna exceed more than number of lags. If it does, then it's just going to the model, simply going to throw the mean value, all right? So I'm going to set my window to this. Let me even call this window 1 because we're gonna have multiple windows, right? So this is the length of the window that I will consider, and these are my coefficients. Model fit, this is model 1. Okay, parameters. Okay, let me run this. So coefficients are the coefficients in front of these error terms. These error terms, these coefficients, okay? So B0 is the first coefficient, and these are the coefficients in front of the error terms. Okay. All right, so we spent some time on this, right? Now it is time for us to use these coefficients to make the prediction. So how are we going to make the prediction? what we're gonna do is we are going to take our, again, remember, please remember, here is how we started. This is the data set that we got, right? And then we added this data set, we added the lagged version of that, right? My data dot shift. So this is what we added, right? Shift. And then, yeah, this is the second step. And then what we did is we separated data into X and Y. Of course, X train and Y train, right? And then X train and X test, let's call it that way. Okay, so this is how we did. And then we created a model and we predicted Y hat, right? Y hat train, right? We predicted that, we predicted Y hat train, and then we calculated the residuals. Minus Y train. This is what we did, right? Now, then we trained a model, trained AR model on residuals. This is where we are now, okay? This is where we are now. So what we're gonna do next is, so this was AR 15, right? 10. So what we're gonna do next is predict residuals from using the model coefficients, Okay, this is what we're gonna do now. We're gonna predict residuals. We are not predicting the original data points. We're gonna predict residuals, and then we're gonna add these predicted residuals to our predictions here. These ones. Again, this is not a very classic time series, what is that, model, okay? But we just want to see the impact of using time series on our earlier model. Okay, so let's predict our residuals using the model coefficients. We already found the model coefficients. So what we want to do is we are going to move using a window, and that window is not going to exceed our number of lags. So we have 10 lags, so that means our window, we are going to make our predictions for the next 10 data points. By the way, are there any? Okay. So could touch base on how a deep learning model handles multiple time series compared to ARIMA models, LSTM or auto. So Rupa, I'm thinking about having a session on LSTMs, maybe at that time, so we can talk about LSTM and autoencoder deep learning models. I used to teach LSTM time series, but it's been a while, so I need to go back and then prepare my notes. And then hopefully we're going to have another workshop on LSTM. I don't understand why we need to separate data to train versus test. Are we dealing with overfitting with ARIMA model like in machine learning? I thought we only have 2 parameters, P and Q. To train and test here, SA, what we are doing is we want to separate our data into train and test. We are going to train a model on the training data set, and then using this window, what we want to do is we want to shift our window, and then the window is going to take some data points from using that window. We're going to make some forecast, and we're going to compare our forecast with our test data set. And then that part of our test data set in the next cycle will become part of our training process. So what we are doing is we first separate train and test, but the test data set slowly going to be eaten up by the training data set. It's going to be part of the training. How predictions got, Aisha, we are, again, remember, this is a very simple model. If you are referring to earlier model, we are using today's data points to make, we are using today's data value as our prediction for tomorrow. It's a very simple model. So what is the temperature going to be tomorrow? Well, my simple answer is, what is temperature today? It's, I don't know, 80 degrees. So tomorrow it's going to be 80. So that is the prediction we use in here. What is the acceptance value of square root of average squared error? So Zhang, there is no clear the one answer for this one, square root of RMSE value. So the accepted RMSE value depends on the range of values your data is taking and the context. Again, giving the example, if you are predicting house prices, and then if house prices are in the range of $1 million to $2 million, if your RMSE is 10,000, your RMSE is 10,000, right? But your house price prediction is $1 million to $2 million. So that is what you're predicting. Then $10,000 up or down is nothing, right? So it's your model is working pretty good actually, right? But if you're predicting, let's say, percentage increase in stock price for tomorrow, right? And then if your RMSE is 5%, that's pretty bad. It's a very bad model, right? So if you think about it, that means that tomorrow's price increase can be, your prediction can be 5% above or below the true value, which is going to be a disaster if it is below, right? How can you tell there is seasonality in the residuals? They seem to randomly up and down around 0 to me. Yeah. So in this case, that's what I said. So I don't see any seasonality here. But if you see a seasonality, so if you see a seasonality in your residuals, then that's an indication that something was missing from your model. But in this case, I don't see, actually visually, I don't see a strong seasonality here. Can you explain why when the forecast horizon is longer than the lags, the model will just predict the average value? Because when it is longer than the lags, you don't, those coefficients are reduced to 0. So you don't have coefficients. Please that. So when you are making the prediction, you are using these coefficients here. You are using these coefficients, right? So above Q. So if you go beyond the lag, then you don't have the coefficients for that. You don't know. So then it's gonna be average. Will you be going through how to use Facebook Profit Library too? Not today, Katie. Not today. Again, that's another good suggestion for future workshops. Again, it's a very large topic, so it's very difficult to actually. Maybe in our next upcoming workshops. Okay. Whenever you estimate, it will be very interesting if you can include PyTorch too. I have read it has become very effective in YouTube. Wow. So okay, so yeah, we can use a lot of people learn deep learning models. That's what I see. It's actually a little bit easier to use Keras when you learn deep learning, but PyTorch is becoming very commonly used in industry. At first it was in the research, but now in the industry too. So let's see when the time comes. Yeah, but why not use PyTorch too? Okay, I hope, again, I'm trying to answer the questions as much as I can. So I might be going a little bit on the surface. How do you observe seasonality by visualizing a graph? Yeah, so what happens is if you see like a cycle, think of this as a sinusoidal wave, let's see, okay? I'm giving you a very exaggerated example. Let's say there is a sinusoidal wave in here. So it's a cycle, right? So it doesn't have to be pure sinusoidal wave. It can be a square wave too. As long as something is repeating itself, right? That is seasonality. And if you see seasonality in your residuals, means what you predicted versus true value. Later on, once you know the true values, things are realized, you know the true values, you compare your predictions with true values, subtracted your predictions from the true values, and then plotted your residuals, and suddenly you see a cycle. That means your model missed an important component in so something you have to go back and then introduce some new variable or consider more number of lags, or actually you need to use instead of Aremax, you need to use Serimax. You need to also consider seasonal lags and seasonal differences in your model. All right. So let's very quickly, time actually is passing a lot quicker than I expected. Let's quickly finish this part. We are going to predict the residuals. So what we're going to do is, let's define this history. So this is going to be our, when I say history, and in most textbooks, you're going to see similar phrases. So we have a train and test data set, but as I said, as we move forward, like let's say I use my training data set to forecast the next 10 data points, okay? And then I make my predictions. And then the next 10 days, I know what happened. Let's say 10 days later, I know what happened, right? Then those 10 days become part of the history, become the training data set. Then I make predictions for the next 10 days, okay? So at this point, my history is nothing but my training data set. So train residuals. Again, remember, I'm making predictions on residuals. So what I'm going to do is, at this point, I'm going to use my training data set, which is going to, so here's just 1 second. I'm going to explain this. Train residual ID minus window. So let's say this is your training data set. Okay, so from data 0, data 1, blah, 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 data, I don't know, 88, data 89, data 90. Okay, so these are your training data points, and your window size is 3. Okay, so what we're going to do is we are going to consider this part as our history for now. Okay, we are going to consider this part as our history, and then we are going to make predictions for here. Then this whole thing will be a part of history, and then we're going to make predictions for D91, D92, and D93. Okay, that's how we're going to proceed. Okay, so this is our history, and let us turn this into a list. And you don't have to turn this into a list, but it's going to be easier for us to later on make comparisons. For I in range length of my history, this is the history. Okay, history I. So I just turned history into a list. That's all. As of now, history is this. I just turned it into a list. Nothing fancy here. Okay, nothing fancy. Okay, so this is my history. Now I want to have my predictions. Okay, let's make this an empty list, and then I have my error, expected error. This is what it's going to be the what is that, the error that I'm going to find by subtracting y hat from true value. Okay, so this is the empty list. All right, now let's begin on the test data set for t in range of my test data set. Okay, again, you don't have to go through all these for loops later, but let us first understand what is going on. Then this is going to be a lot more interesting later. So for now, it's actually a little bit boring. So we are going through our test data sets. So what's going to happen is we are going to make our predictions for these test points. Okay, again, given, let's say this is the history that we know. Now, how about 91? What is the data for 91? What is the data for 92? Okay, so this is what we want to predict. Or what is the data for 120? Okay, so these are what we want to predict. But because we are training a model, we actually know what is data 91. We have the data for that. We have the data for data 92, and then we have the data for data 120. Okay, so what we're going to do is we are going to make a prediction, and then we are going to compare that with the true value. That's what we're going to do. So our prediction for this guy is actually going to be what we have today. Okay, so our prediction for 91 is what we have at 90, right? So what is the tomorrow's temperature? It's today's temperature. So that's why I'm going to use test xt. Okay, so this is my prediction for y hat, and then my error is y hat. I'm going to subtract y hat from the true value. Okay. Please keep in mind we already shifted x, and that's how we created y. Please keep that in mind. So even though they are tt, this y value is xt plus 1. Okay, please keep that in mind. All right. We already shifted that earlier. Okay, and then this is the error that I find from the model. And then I'm going to just add this model into expected error, append this error. Okay, so we got these errors. Now, this is what we did earlier. Now what I'm going to do is I'm going to use the lags and the coefficients that we found, and then I'm going to make predictions for the errors. So this is the true error, and then I'm going to make my prediction on these errors. So for that, I'm going to use my historical data set. Okay. So this is the amount of training data points I have. And then from this history, what I'm going to do is I'm going to create a list. So I in range length minus window length. History I. I'm going to explain what this means. For this is history I. And this is equal to that. Okay. So remember, we found these coefficients, right? We found these coefficients. So what we're going to do is, for example, error, again, remember, these coefficients are for predicting the error. Error at t plus 1 is equal to this coefficient. Okay, this coefficient, let me put it here, plus this coefficient times, I'm sorry, this coefficient times error at t, okay, plus this coefficient. That is what's happening when you are running MA or AR model. So that's why I've tried to spend time here explicitly show you what is happening, t minus 1, okay? So to find the error for the next time period, I'm using the error from now and error from previous periods. How many error terms I'm going to consider? I'm going to consider I'm limited with this number of lags. So that's what I'm going to do. What is window? Remember window? Window is the number of, I define window here. Yeah, window is number of lags. So let me use window 1 actually here. Window 1, okay, and then window 1. So what I'm doing is this lag is my historical data, which is the historical data is here, the error terms from previous periods. I am just taking 10 of them here. Window 1 is 10. I'm actually taking 9 of them here because length is not included. I'm taking 9 of them here, and then I'm going to multiply them by their coefficients. Okay, so let's do it. Let's do it very quickly. So this is the prediction of my error. That is what I predict. And then remember, these coefficients are equal to coefficients. So the first term is coefficient 0, which is this one, okay, coefficient 0. And then I'm going to run a for loop. Again, very long, but I think it's going to tell us what's happening inside. Okay, I'm going to run this for loop, and then this for loop is going to run through this window. Okay, again, window 1, because I called it window 1, right? So what is window 1? Remember, that is the length of my coefficients. That is the length of my coefficient. Where is it? It's right here. Length of my coefficients. So let's see what window 1 is. 10. Okay. So so the 10th one will not be included. That's right. I have 9 lags, right? 9 lags. The first one is already here. Okay. So pred error is equal to, like, pred error plus the coefficient from d plus 1, because the 0 was used. Now I'm using the first one, times lag. This lag is, remember, from our historical data set. I took the last 10 data points from my training data set. The last 10 data points from my training data set. I'm using them to multiply them by coefficients to find the next data point. Okay. So lags, this is going to be window 1 minus d minus 1. Okay, perfect. So here is what I'm doing here. Let me write this one more time here using the coefficients. This is coefficient 0. This is coefficient 1. Okay, times this error t is, now I'm using this notation here. Okay, it is lag. In this case, d is 1, window is 10, 10 minus d minus 1. So I'm using lag 9. Okay, lag 9. And then this is coefficient 2. I'm using lag 8. I'm almost done, okay? So hopefully this is making sense to us. So I'm multiplying past error terms with their corresponding coefficients. And then I'm just adding those multiplications here, these multiplications, that is going to make my prediction. All right, we're done, right? So we got the prediction. Now I'm gonna just add prediction. So predictions is an empty list. Predictions, I'm just going to append this with red error. Okay, perfect. Now I think we are done. Train res ID. Of course, we need to run this part. Train res ID. Where is it? This is history. Yeah, I didn't define train. I think I defined it somewhere, but okay. Somewhere here. Sorry, guys. So it's been a lot of things that. Anyways, let me write it one more time. I remember writing that history train res ID. Anyone sees train res ID where we defined it? Anyways, let's just write it here. Train res ID. Yeah, I think this should be a list. Find it so that I'm not gonna write anything. Oh, train y train y I minus my predictions, right? So whatever the train predictions we found earlier, I think we found them, prediction I, for I in length of train predictions. So this is basically the difference between my predictions and let me see if I have train predictions. Yeah, they are here. And put this. These are my predictions for the training data set. I got it. Okay, I in, oh, it should be range. Yeah. Okay, we got the train residuals. And then what now? List object is not callable. History. This is the range. Oh, history I. Yeah. Okay. History I, length is not defined. Sorry guys, so I just jumped from here to there, so I sometimes miss what I wrote where. So I'm just let me see. Yeah, length is the here. Length is length of the history. Length. Okay, finally. So these are the predictions. Let's just plot it. Okay, let's just plot it. PLT. I hope you were able to follow me. This is the prediction. These are the expected predictions, the true predictions, and this is the what is that? Predictions. Or is red? Okay, so I made a small mistake, so I'm just trying to find where I made a mistake. Predictions, expected error, length. This is the lag. This is coefficient. Predictions. Why predictions are coming as negative? This is 0 here. Should be 0. Predictions. Okay. Predictions. Okay. All right, so something that I don't see, I made a mistake here. I'm trying to find out what is that mistake. Coefficient d plus 1 times lag of window 1 minus d minus 1. So that I made a mistake, but I cannot actually see what mistake I made. If you can see it, please let me know. Please let me know. Okay. So let me see what is lag. These are the lags. Okay, lag is fine. Okay, let's see coefficients. Okay, these are the coefficients. All right, the last value is 9. Okay, and then window 1. Yeah. Okay, everything looks fine. Thread error is this, and predictions is an empty. Yeah, I don't see the mistake I made. Sorry, let me check if you guys saw it. There is a misspell word in a list comprehension history. It's residuals. You did not use train res ID. Okay, let me see. Test YT. Okay, length window. Let's see. Okay, let's see. So I'm using the train res ID. The history is the train data set. Okay, all right. And then I created the history. All right, it is also fine. And then I used this length of history. So this y hat is this. This is also correct. Yeah, expected. This one was also correct. I used the history length, and then from here, this is history of I for I in range length minus window 1 and length. So this also is correct. And then pred error is coefficient 0. Something is happening here. Pred error is equal to coefficient of d plus 1 times lag of window 1 minus d minus 1. Okay. So normally what I'm supposed to get, I just don't want to waste your time. So here I did this before multiple times before the class too. Here I was supposed to get the error terms predicted, but it was not so well. So there is one small thing that I couldn't see here. I don't know what that is, but there is one small thing that I cannot see it. Predictions. Yeah, there's one small thing that's, I'm sorry, I cannot see it now. If you can see it, I can correct it. Spelling of length. Yeah, I corrected that one. Need to make pred error equals 0. Yeah, that is right. It didn't work. Pred error equals 0. Then this, no, because there is no need because I've already initiated here, right? Every time I initiate it. right? Every time I'm initiating it. So there is no need for that. Something is not working. I cannot see it. I'm sorry, I cannot see it now, but there must be a very small thing that is not working. Let me open my own file that I prepared before the class. Every time I have my instruction file, which I prepared before the class, like 3 hours ago. So let me show you what I found. This, okay, so it should be this. Thread error. Okay, let me see. I'm doing some, again, look, it's not so different than what I have. I'm doing the same thing. Let me see. Thread error is coefficient. Thread error is coefficient v plus 1 times, again, window minus d minus 1. So there isn't any, I don't see any error. Sorry, I cannot see any error. I'm pretty sure that after the class, I'm going to find it out very quickly. But this is how it looks like. Let me go through my file. Let me not waste your time. So this is how it's going to look like. Okay, so this is my true error, and this is my predicted error. All right, I'm going to share this file with you too. So don't worry. Okay, don't worry. Lag window, yeah, I used, in the class, I used window 1 instead of window. Sometimes I type things differently, but it's okay. So there is one small mistake that I couldn't see. I'm going to find it later. Let me go through this file with you, and then let me share this file with you, and you can work on this file yourself. So what I did next is, remember, this is the error terms. The red lines are my predictions for error terms. What I did next is I just added my error predictions with my predictions for y hat. And this is the best I could get. Okay, this is the best I could get given this data. Remember, let me go back here. So this is what I did next. Gave you the list of what, yeah, here. So this is the flow of things that we did. We predicted residuals. Next, we added our y hat. Remember, y hat was our y hat train. We added y hat with our predictions of residual. In other words, we predicted the errors, and then we added errors with our predictions for that we made earlier. Okay, so this is where we are. This is what we did here. This is what I did. Okay, all right. So then what I did was, these are some stuff that I tried to implement. Let me see. Yeah. Next, what I did is, you know what? Let me not go through this y hat and residual prediction stuff. Okay, let me not do it that way. So what I did is, no. Let me, so here, what I did is I used ARIMA model on the residuals. Again, still residuals, but I used ARIMA model on the residuals. So, okay, let me see. Yeah, I'm trying to remember what I did. So here is our original data set. This is the original data set that we read. Okay, this is daily birth numbers. I didn't shift anything. I just, this X is the following, this one. The original data set, this one. Okay, this one. Okay, this one. Remember, to find some predictions, we shifted this by 1, added another column. So here I'm not doing that. Here I am not doing that. Okay, what I'm doing instead is I'm using an ARIMA model. So in the ARIMA model, now we have some idea about what AR means. We have some idea about what MA means. So what I did in here is, instead of taking the difference by 1 day, remember I took the data for the time series data set, and then I shifted it by 1, right? That's what I did. So instead of doing that, what I did is I took my data set, split it into train and test without, again, shifting or doing anything. And then this time, instead of an AR model, I focus on an MA model. Again, MA model is moving average model, is nothing but predicting. This is MA model. 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 Okay, this is MA model, and that's what we did. It's an AR of error terms plus a constant equals the data point now. Okay, at time t. This is MA model. It is auto regression of. It looks like an auto regression of error terms. It's not, of course, auto regression because YT is not a regression of error terms. But I mean, it's not auto because YT and error terms are two different things. But if you consider this error term part, as we did now, right, earlier, I can create an AR model for the error terms only. Instead of doing that, instead of creating an AR model for the error terms, we use error terms as part of the model, using error terms to predict the data point YT. Okay, instead of predicting error T, I'm predicting YT using the error terms. That is moving average. Okay, that is moving average. So that's why I said, you know what, let's not do it that way, but instead use ARIMA directly. Okay, so here, this one, 8 is, I used 8 legs. I used 8 error terms going back. Error T minus 1, T minus 2, T minus 3, T minus 8. Okay, I used 8 error terms. In addition to that, I also took one difference of my data. That means I took my data. Okay, I took my data, I shifted it as I did earlier, and then take the difference. Okay. In other words, I used YT plus 1 minus YT. Okay, that's what I used. And this is my RMSE. It is 7.2. Remember earlier it was 8.5. I'm doing better here. And this is how my prediction looks like. Okay. And then I said, there is something wrong in here. Okay, so yeah, I can predict all this. But it's almost like I am predicting the mean of the trend, okay? But I'm not predicting these values here, okay? Something is wrong, something is missing. Right? So these parts are not in the textbook. I just played around with the data set, okay? So you can do it yourself if you like. So another thing I tried is, again, took the original data set. This time, I didn't shift my data. I didn't take the first difference. I didn't do that. What I did is, oh, by the way, something missing here means I took one thing that might be the case, that I took difference. So that might have some impact. I didn't explore it. But what I did here is, I took my original data set. I didn't shift, or I didn't subtract YT plus minus YT. I didn't do that. And then I only considered 3 legs for the MA model. In other words, error term from -1, -2, -3. And this was my prediction. Okay, so this prediction, it looks much better than the earlier cases. But if you look at the RMSE value, it's pretty high, right? Earlier RMSE values were lower. So here, what makes it look like better is it is now capturing these rises and increases, like ups and downs, right? But there is a systematic difference between the original data set and my predictions. It's almost like if there was a way for me to shift this red data points up, the predictions up a little bit, then this RMSE would get much smaller and my predictions would look much, much better. Okay, so then I thought, what is missing here? So what else can I do? So one thing I did is I looked at the original data set. I went back to this birth data set. And then I tried to see if there are some small seasonalities that I am missing. The reason why I thought about this is because, remember, when we looked at the autocorrelation function, we noticed this one, right? So this autocorrelation is somehow, it's like some small cycle here. I mean, it's not pure season, but there is something is repeating itself. It looks like that way. The autocorrelation function, you see, it goes down and then goes up, goes down, like almost like exponentially, and up. Here I lose it, but here again, right? So that's why I said maybe there is a way to improve this model a little bit. Another thing I did is, again, I'm going to share this code with you. So I was planning to talk about how you can aggregate your data by day or by week or by month. So that's what I did this for you. So I'm going to share this code with you. You can run it yourself. So what I did is I took all this data set and then I added them up by the days of the week. Okay, like Friday. So it's a little bit interesting that on Sundays, the birth numbers are getting down on average, and then it begins to increase again. Okay, so this again made me think that there might be some weekly cycle, something, right? So something is happening like every week. It's the birth numbers are going down on through Sunday, and then it is going up. Maybe after Wednesday, again, it begins to go down, and then it goes up, right? So, by the way, these numbers are these days are not following the order. So I need to put them in order, so it's gonna look much better actually. And then what I did is I also looked at the months. Okay, I also looked at the months, and then I see like, oh, here every 4 months it looks like something is repeating, but again in the last quarter the season is the seasonality is not there anymore. Okay, but these two again makes me think that there is something going on. Okay, there is something. But so Michael is saying, are women, pregnant women choosing elective C-sections delivery on weekends? Maybe, I don't know. Maybe, might be. Okay, so given all that, again, these are just exploration of data set, guys. Nothing certain. I just did this this morning. Okay, so I didn't really spend too much time. I just did this morning. So I just wanted to see if there is something I can find from this data set. And finally, this is the final model. What I did is I used Serimax. So this S is standing for seasonality. ARIMA, this MA part which we're gonna use. So what, again, I didn't explore this thoroughly. Okay, so I think I should change these parameter values a little bit more and then optimize it. But this is my original model. Remember this guy, this model here, this model. Again, visually it looks better than the previous models, but there is a large RMSE difference because it looks like this whole thing should shift up. Okay. And then this is the last thing I tried. So what I did is I thought maybe there is a seasonality too. There is some seasonality every 7 days. So weekly, every 7 days, there is some cycle going on. Again, this is not certain. I just made it up. And then I used one lag. Okay, one lag. So that means every week I'm going to consider for each week. So if you are Monday, I'm going to consider the last week's Tuesday. Okay, that's what it means. Okay, again, the RMSE is not so good. It's not better than what we found earlier. RMSE is better than this one. RMSE is better than this one. Where is it? This one. Okay, root mean squared error, but it is not better than our previous models. We should look at this one. It's 7.499. Okay. It's pretty good. 7. If you compare this with this more sophisticated model, right? But again, I'm pretty sure we can improve this model. There is something going on here that I need to. I tried many different things. I tried to see if there is a constant trend here or a time-dependent trend that we are missing. I tried all that too. So I changed these parameter values too. Anyways, I was not successful in filling this gap. But I think it's just a matter of one or more two more trials, so which we can find the value. So that is what I prepared. This is the first part. And could we add the difference of mean between prediction and actual set, and that can be constant we add to the prediction? That might improve RMS. So again, difference of mean between prediction and actual set. So you can add this pre-NH. Yeah, that's one thing to boost this prediction up is. Again, you cannot do this for future data points, but historically you can find that if there is any systematic shift between your predictions and actual data points, you can find that, take the mean value, and then add that up with your future predictions. That might, I'm pretty sure that's going to have a good impact. Actually, it's going to, at least it's after the first couple of windows, it's going to close the gap between. It's going to decrease the gap between your predictions and true values. But I was looking for a different solution as part of time series model. Okay, so I didn't want to do anything from outside. So I thought similar things, but I didn't want to do anything from outside. I was trying to fix the problem using time series model. Yeah. Okay. Thank you so much for the suggestion. So this is the first file. The second file was actually more interesting than this one, but I don't think we have time. I'm really tired, so I don't think we have time to go over the next one. But let me show you the next one. I'm gonna share this one with you too. So the next one, I got this from a textbook, but I changed the code so that you can do things a little bit manually. So it's gonna be an exercise for you. So it's you're not going to automatically use the what is that? So in the textbook, the person was introducing all these indices. They were not dates actually. So I tried to introduce you how you can create a sequential dates from, let's say, this is the starting date 2019-0101. Can you create 500 dates following this day? 500 sequential days following this day? So the answer is yes, you can do that. And then here, that's what we are doing. And then can you make this the index of data sets? So that's what I wanted to show you actually as part of this. So this is how the textbook did, but I actually preferred doing this a little bit differently. Okay, so, and then I also included, so these were not there, so I spent some time on this. So when you are plotting time series data sets, how you can play around with these X ticks. So it may not be so important at first, but when you are visualizing your results, these are becoming important. So that's why I spent some time on, can you take the months? For example, these dates are looking this way. So can you take the month and then year and then make it X tick? Okay, so that's what I tried to show you. Here, the data set is clearly not stationary. As you see, the data set is increasing, right? So there is an increasing trend. It's not stationary. So that's what we found in here. We looked at the p-value is 0.52. We implemented ADF test. It's not stationary. So what we did was we took the difference. When the data set is not stationary, the first reaction is taking the difference. Taking the difference is going to most likely make the data look more stationary. Actually, that's what we did, taking a difference and then plotting the difference. So this is difference, not the difference means YT minus YT plus 1 minus YT. Okay, that is the difference. So the difference doesn't look like the original data set, right? So now there is no that uptrend. It looks like this is stationary. It looks like, again, running the ADF test gives us actually a good idea that it is actually stationary, right? And then check the autocorrelation function. As you see, autocorrelation drops abruptly after the first three. Remember, autocorrelation plot. If your if autocorrelation values drop abruptly after a certain number of lags, this is a good indication that this is an MA model, okay, moving average model. If the lags are slowly decreasing, it's a good indication that you're supposed to use an AR model. In that case, you have to check your PACF plot and then see how many lags are statistically significant. That will define the p-value for your AR model. Okay, so here again, I split the data into train and test. Okay, and then here is how the data itself looks like and how the difference looks like. And then this time I used Cerimax. Okay, and then I used an MA model of lag 2 because of this one. Actually 0, 1, 2. Okay, so that's why I used lag 2. And then here there are 3 predictive models. The first one is simply using the mean. Actually, I was planning to talk a lot in more detail about this one because the way Cerimax model is this part. maybe a little bit confusing to you if you are learning this the first time. It may be confusing to you. So I was planning to talk a little bit more about this one. For example, here is the model. This is the data sets, okay, training data sets. And again, we are training this model as we shift the window. And this is the number of legs for our MA model. Here I'm fitting the model. Then I'm getting the predictions. So this get prediction is not going to give you numbers. It is an object, like group by in pandas. It's an object. So you need to take this object first. And then on this object, you need to apply a function like predicted mean. That is going to give you the predictions. Okay, so this part was not easy to see at first if you are learning the first time. So I'm sorry, I couldn't. I really wanted to spend time on this, but I don't think I will be able to do that. So here there are 3 different predictions. So all that I prepared for you. So this will be yours, so you can play around with that. So this is the green one is the mean. It's using the mean value. Red one is using the last value as your prediction for the next one. It's like I'm using the value on time t as my prediction for time t plus 1. Okay, red one, and then the black one is actually the moving average model. Okay, moving average model. So if you look at the RMSE, where is these are the RMSE. Let me see. Hold on. No, it's not this one. RMSE. Where is the RMSE? Yeah, these are the RMSE. Right? Yeah, this is MSE actually, minimum squared error. You see that MA model is giving you the best result in this case. Okay, MA model is giving us the best results in this case. And this was, again, this is the prediction, and this is the true value. So one thing about this one, let me see. Not so important. We just here zooming into data set. That's all. Nothing mysterious here. Okay, let me stop here, guys. Let me stop here. I'm still puzzled with why the code did not work for earlier case. I'm gonna find the reason, probably some small mistake. I'm going to upload solutions. So as of now, you have empty files. I know that. I'm going to upload these 2 to GitHub. So you have access to this. Again, please just spend your time to play around with the code. If you don't write the code, it's very difficult to understand what is going on, actually. Yeah, it's very difficult. Thank you for listening. I'm going to stop here. I'll see you guys maybe in next workshops. Thank you for stopping by and for listening. Take care. Okay, bye.